These represent two established timebank communities. Though each is active and internally consistent, they are separated by a void in the network. Independent timebank deployments exist as isolated databases. By default, they lack the technical capability to share state or recognize users from external deployments. To bridge these nodes, Project NEXUS utilizes a specific engineering protocol, the Federation API. A secure connection depends on a system capable of handling two distinct types of data: intentional user queries and immediate, unprompted domain events. This requirement leads to a dual-channel architecture. The connection between Node A and Node B is split into two pathways. The first is a synchronous API layer for intentional state queries. The second is an asynchronous webhook layer designed to transmit real-time events, like private messages. This dual-channel approach allows independent platforms to exchange data through purpose-built pathways, providing a framework for interoperability without a central master server. The synchronous API layer executes exclusively when one platform makes an intentional request for data. This inbound routing manifold directs requests to three protocol-specific controllers. The Federation controller processes JSON payloads, authenticated by a bearer API key against the local database. Meanwhile, the Federation Communitin controller strictly requires the JSON API standard, checking the application/vend.api plus JSON MIME type before parsing. Outbound calls follow a similar logic, routed through the internal Federation external API client. The client resolves the correct protocol adapter by checking the protocol_type field stored in the external partners table. For all inbound requests, the Federation API middleware manages the authentication lifecycle. API keys are never stored as plaintext. They are protected by SHA-256 hashing with Q hash column. These endpoints utilize X-rate limit headers to throttle traffic, returning a 429 status code if a partner exceeds their request window. The system also supports short-lived authentication by issuing a 1-hour JWT, where the subject maps to the verified partner ID. While this synchronous layer is secure for manual requests, it is inefficient for the real-time state updates required by modern time banking. Direct messaging or transaction cancellations cannot rely on synchronous requests. If one side needs to know something immediately, waiting for the next data pull is too slow. Relying on polling creates a loop. Node A repeatedly pings Node B for updates, quickly generating a stack of 429 error responses. The webhook architecture removes this need. Instead, Node B independently pushes a single data packet the exact moment an event occurs. These webhooks are triggered by Laravel domain events within the host application. For instance, a message sent event triggers the push federated message to partners listener to alert the receiving platform. A listing published event triggers a similar listener to synchronize the new offer across the network. To prevent external network delays from slowing down the local user, these listeners implement the should queue interface, allowing background workers to handle the delivery. This background processing also handles scenarios where the target server is temporarily offline. The queue utilizes exponential backoff to retry failed deliveries, while a circuit breaker prevents the system from hammering a non-responsive partner. Pushing queued events through these fault-tolerant workers ensures that cross-platform state stays updated without compromising local system performance. Webhooks introduce a unique security problem. How can a server verify an unprompted inbound request that doesn't use a standard session password? Security here relies on cryptographic signatures that prove the request originated from a trusted partner. Validation requires an HMAC SHA-256 signature built from 5 components: the request method, path, timestamp, unique nonce, and raw payload body. The receiver recalculates this signature using a secret key. If the local hash matches the incoming signature, the payload is verified as untampered. However, even a valid signature can be intercepted and resent in a replay attack. The first defense is the timestamp, which the system uses to enforce a narrow 5-minute validity window for any incoming webhook. The second defense is the unique nonce, which is cached in the Redis database. If a request arrives with a nonce that has already been seen, the middleware immediately rejects it. Combining these temporal and caching constraints ensures that every push-based update is as secure as a standard password-protected request. Beyond network security, the system must enforce internal rules to determine which data is allowed to leave the database. To maintain strict multi-tenant isolation, federation permissions are stored separately from the standard tenant feature set. This authorization schema uses 3 distinct tables, acting as mandatory gates for every federated action. The top federation_system_control table is the global kill switch. If disabled by the superadmin, all federation traffic across the entire platform stops instantly. The federation_tenant_whitelist acts as the second gate, requiring that each individual tenant be explicitly approved for federation before they can connect to a partner. The final gate is Federation Tenant Features, where the admin controls specific capabilities, such as allowing messaging while blocking time credit transfers. The Federation Feature Service ensures that updates to these permissions are written to all 3 tables atomically to prevent configuration desync. Once authorized, the system performs an initial data backfill using the pull members and pull listing services to catch the new partner up to speed. This layered schema ensures that a tenant can only share exactly what has been authorized by both the platform admin and the individual tenant admin. While the database gates control what a tenant can do, the final decision remains with the individual member. To function effectively, the system must also bridge user reputation and trust scores across platforms. Federated ratings are stored with an isFederated flag set to 1, identifying them as external contributions. The member ranking service then uses the Receiver Tenant ID scope to aggregate these ratings, ensuring a member's reputation persists even when they trade with a partner on a different server. All of this is gated by a single Boolean flag, users.federation.optin. If a member has not opted in, the database will not transmit their profile, listings, or messages, regardless of any other settings or cryptographic signatures. The NEXUS Federation API links separate instances through synchronous logic and asynchronous event handling, ensuring that every data exchange remains bound by cryptographic signatures and the explicit consent of the individual member.